Reinforcement learning is a fascinating branch of machine learning where an agent learns to make decisions by interacting with its environment. Unlike supervised learning, where the model learns from labeled data, reinforcement learning relies on a system of rewards and penalties to guide the agent toward the best possible actions. Imagine teaching a dog tricks. You reward it for good behavior and discourage unwanted action. Similarly, in reinforcement learning, the agent receives positive or negative feedback based on its actions, gradually improving its performance over time. This approach is widely used in robotics, gaming, and even finance. Let's dive deeper into how this process works and why it's so powerful. The heart of reinforcement learning are two main components: the agent and the environment. The agent is the learner or decision maker, while the environment is everything the agent interacts with. The agent takes actions within the environment, and the environment responds by providing feedback in the form of rewards or penalties. This cycle continues, allowing the agent to learn which actions yield the best outcomes. Think of a video game character navigating a maze. The character agent moves through the maze environment, receiving points for reaching goals or losing points for hitting obstacles. This dynamic interaction is key to reinforcement learning. Reinforcement learning, the agent operates in a world defined by states and actions. A state represents the current situation or context the agent finds itself in, while an action is a choice the agent can make. For example, in a chess game, a state could be the arrangement of pieces on the board, and an action would be moving a piece. The agent observes the state, selects an action, and then the environment transitions to a new state. This continuous loop of observing, acting, and transitioning is fundamental to how reinforcement learning works. Rewards and penalties are the core motivators in reinforcement learning. When the agent takes an action, the environment provides feedback in the form of a reward, positive feedback, or a penalty, negative feedback. This feedback helps the agent understand which actions are beneficial and which are not. Over time, the agent learns to maximize rewards and minimize penalties, improving its decision-making skills. This trial and error process is similar to how humans and animals learn from experience, making reinforcement learning a powerful tool for developing intelligent systems. Learning process in reinforcement learning involves the agent exploring different actions and learning from the outcomes. Initially, the agent may make random choices, but as it gathers more experience, it starts to favor actions that lead to higher rewards. This process is called exploration and exploitation. Exploration allows the agent to try new actions, while exploitation means choosing actions that have worked well in the past. Balancing these two strategies is crucial for effective learning and achieving optimal performance. Policy and reinforcement learning is essentially the agent's strategy for choosing actions. It's a mapping from states to actions, guiding the agent on what to do in each situation. The policy can be simple, like a set of rules, or complex, like a neural network. The goal of reinforcement learning is to find the optimal policy that maximizes the total reward over time. As the agent learns, it updates its policy based on the feedback it receives, gradually improving its performance and decision-making abilities. Value functions are a key concept in reinforcement learning. They estimate how good it is for the agent to be in a particular state or to perform a certain action. In other words, value functions help the agent predict the long-term rewards it can expect from different choices. By evaluating the value of states and actions, the agent can make better decisions that lead to higher rewards. This predictive ability is what enables reinforcement learning agents to plan ahead and act intelligently. Q-learning is one of the most popular algorithms in reinforcement learning. It helps the agent learn the value of taking a certain action in a given state, known as the Q value. The agent updates its Q values based on the rewards it receives, gradually building a table of the best actions for each state. Q-learning is powerful because it doesn't require a model of the environment, making it suitable for a wide range of applications, from robotics to gameplay. Deep reinforcement learning combines reinforcement learning with deep neural networks. This allows agents to handle complex environments with high-dimensional data, such as images or sensor readings. By using deep learning, agents can learn directly from raw inputs, making them capable of solving tasks that were previously too difficult for traditional methods. Deep reinforcement learning has achieved impressive results in areas like playing video games, controlling robots, and even managing resources in data centers. Central challenge in reinforcement learning is balancing exploration and exploitation. Exploration involves trying new actions to discover their potential rewards, while exploitation means choosing actions that have already proven to be effective. If the agent explores too much, it may waste time on suboptimal actions. If it exploits too much, it might miss out on better opportunities. Finding the right balance is crucial for the agent to learn efficiently and achieve the best possible result. Reinforcement learning problems are often modeled as Markov decision processes, or MDPs. An MDP provides a mathematical framework for modeling decision-making situations where outcomes are partly random and partly under the control of the agent. It consists of states, actions, rewards, and transition probabilities. By using MDPs, researchers can analyze and design reinforcement learning algorithms more effectively, ensuring that agents can learn optimal strategies in a wide range of environments. Reinforcement learning has revolutionized robotics by enabling machines to learn complex tasks through trial and error. Robots can now learn to walk, grasp objects, or navigate environments without explicit programming. By receiving feedback from their actions, robots gradually improve their skills, adapting to new situations and challenges. This ability to learn from experience makes reinforcement learning a powerful tool for developing intelligent, autonomous robots. One of the most famous applications of reinforcement learning is in gaming. AI agents have learned to play complex games like chess, Go, and even video games at superhuman levels. By playing millions of games and learning from each move, these agents develop sophisticated strategies that often surpass human capabilities. Reinforcement learning has not only advanced the field of artificial intelligence, but also provided valuable insights into decision making and strategy development. Finance, reinforcement learning is used to develop trading algorithms that can adapt to changing market conditions. These algorithms learn to make buy or sell decisions by analyzing market data and receiving feedback on their performance. Over time, they optimize their strategies to maximize profits and minimize losses. This adaptive approach allows financial institutions to stay competitive in fast-paced markets and respond effectively to new trends. Reinforcement learning is making waves in healthcare by helping design personalized treatment plans and optimize medical procedures. For example, algorithms can learn the best sequence of treatments for patients with chronic diseases, improving outcomes and reducing costs. By continuously learning from patient data, these systems adapt to individual needs, offering more effective and efficient healthcare solutions. Self-driving cars rely heavily on reinforcement learning to navigate complex environments safely. These vehicles learn to make decisions like when to accelerate, brake, or change lanes by interacting with their surroundings and receiving feedback. Over time, they become better at handling real-world situations, such as avoiding obstacles or responding to traffic signals. Reinforcement learning enables self-driving cars to continuously improve their performance and safety. Reinforcement learning is also used for resource management in areas like energy, logistics, and data centers. Algorithms learn to allocate resources efficiently, reducing waste and improving performance. For example, in data centers, reinforcement learning can optimize the use of servers to save energy and reduce costs. This ability to adapt to changing demands makes reinforcement learning a valuable tool for managing complex systems. Many online platforms use reinforcement learning to provide personalized recommendations. By learning from user interactions, these systems suggest products, movies, or content that match individual preferences. The more users interact, the better the recommendations become. This approach enhances user experience and increases engagement, making reinforcement learning a key technology in e-commerce and entertainment. Despite its successes, reinforcement learning faces several challenges. One major issue is the need for large amounts of data and time to learn effective strategies. In some cases, the agent may struggle to explore enough or may get stuck in suboptimal behaviors. Additionally, designing appropriate reward functions can be difficult, as poor rewards can lead to unintended consequences. Researchers are actively working to address these challenges and make reinforcement learning more robust and efficient. Sample efficiency refers to how quickly an agent can learn from limited data. In many real-world applications, collecting data can be expensive or time-consuming. Improving sample efficiency is a major research focus in reinforcement learning. Techniques like experience replay and transfer learning help agents learn more effectively from fewer experiences, making reinforcement learning more practical for real-world use. Reward shaping involves designing reward functions that guide the agent toward desired behaviors. By providing intermediate rewards for progress, rather than just final outcomes, agents can learn more efficiently. However, poorly designed rewards can lead to unintended behaviors. Careful reward shaping is essential for ensuring that agents learn the right strategies and achieve the intended goals. Effective exploration strategies are crucial for reinforcement learning agents to discover the best actions. Techniques like epsilon greedy, softmax, and upper confidence bound help agents balance exploration and exploitation. By trying new actions in a controlled way, agents can avoid getting stuck in suboptimal strategies and improve their overall performance. Some scenarios, multiple agents interact within the same environment, leading to multi-agent reinforcement learning. These agents may cooperate, compete, or both, creating complex dynamics. Multi-agent systems are used in areas like traffic management, team sports, and distributed robotics. Understanding how agents interact and learn together is an exciting and rapidly growing area of research. Transfer learning allows reinforcement learning agents to apply knowledge gained in one task to new, related tasks. This can significantly speed up learning and improve performance, especially in environments where data is scarce. By leveraging previous experience, agents become more adaptable and efficient, making transfer learning a valuable technique in real-world applications. Imitation learning is a technique where agents learn by observing and mimicking expert behavior. Instead of learning solely from trial and error, the agent uses demonstrations to guide its actions. This approach is especially useful when exploration is risky or expensive. Imitation learning is widely used in robotics, where agents can learn complex tasks by watching humans perform them. Reverse reinforcement learning focuses on discovering the underlying reward function by observing the behavior of experts. Instead of specifying the reward function directly, the agent infers what motivates the expert's actions. This technique is valuable for tasks where it's difficult to define rewards explicitly, such as driving or medical procedures. By understanding expert motivations, agents can learn to replicate complex behavior. Policy gradient methods are a class of reinforcement learning algorithms that optimize the policy directly. Instead of estimating value functions, these methods adjust the policy parameters to maximize expected rewards. Policy gradient methods are particularly effective in environments with continuous action spaces, such as robotics and control systems. They have enabled significant advances in training agents for complex tasks. Actor-critic algorithms combine the strengths of value-based and policy-based methods. The actor decides which action to take, while the critic evaluates how good the action was. By working together, these components enable more stable and efficient learning. Actor-critic methods are widely used in deep reinforcement learning and have achieved impressive results in various domains. Temporal difference learning is a key technique in reinforcement learning that combines ideas from Monte Carlo methods and dynamic programming. It allows agents to learn directly from raw experience without needing a model of the environment. By updating value estimates based on the difference between predicted and actual rewards, temporal difference learning enables faster and more efficient learning. Monte Carlo methods are used in reinforcement learning to estimate value functions based on averaging returns from multiple episodes. These methods rely on complete episodes of experience, making them suitable for environments where episodes naturally end. Monte Carlo techniques are simple yet powerful, providing valuable insights into the long-term consequences of actions. Dynamic programming provides a set of algorithms for solving reinforcement learning problems when a model of the environment is available. Techniques like value iteration and policy iteration use recursive equations to find optimal policies. While dynamic programming is powerful, it can be computationally expensive for large or complex environments. Nonetheless, it forms the theoretical foundation for many reinforcement learning algorithms. Function approximation is used in reinforcement learning to generalize from limited data. Instead of storing values for every possible state, agents use mathematical functions or neural networks to estimate values. This approach enables reinforcement learning to scale to large and complex environments, such as video games or real-world robotics, where the number of possible states is enormous. Hierarchical reinforcement learning breaks down complex tasks into simpler subtasks, making learning more manageable. By organizing actions into hierarchies, agents can solve problems more efficiently and reuse learned skills in different contexts. This approach is especially useful for tasks that require long-term planning or involve multiple steps. Reinforcement learning can handle both continuous and discrete action spaces. In discrete action spaces, the agent chooses from a finite set of actions like moving left or right. In continuous action spaces, actions can take any value within a range, such as adjusting the speed of a car. Different algorithms are suited to each type, and choosing the right approach is important for effective learning. Reinforcement learning algorithms can be model-based or model-free. Model-based methods build a model of the environment and use it to plan actions, while model-free methods learn directly from experience without a model. Each approach has its advantages and challenges. Model-based methods can be more sample-efficient, but building accurate models can be difficult. Model-free methods are more flexible but may require more data. Safety is a critical concern in reinforcement learning, especially in real-world applications like healthcare or autonomous vehicles. Safe reinforcement learning aims to ensure that agents avoid dangerous or undesirable behaviors while learning. Techniques include adding safety constraints, using risk-sensitive rewards, and monitoring agent actions. Ensuring safety is essential for deploying reinforcement learning in sensitive domains. Human-in-the-loop reinforcement learning involves humans guiding or correcting the agent during training. This approach can speed up learning, improve safety, and ensure that agents learn desired behaviors. Human feedback can come in the form of demonstrations, corrections, or rewards. Combining human expertise with machine learning leads to more reliable and effective agents. Deploying reinforcement learning agents in the real world presents unique challenges. Agents must handle uncertainty, adapt to changing environments, and interact safely with humans and other systems. Testing and validation are crucial to ensure reliable performance. As reinforcement learning continues to advance, more applications are emerging in industries like manufacturing, transportation, and customer service. Ethics play an important role in reinforcement learning, especially as agents become more autonomous. Issues like fairness, transparency, and accountability must be addressed to ensure responsible use. Researchers are developing guidelines and frameworks to promote ethical reinforcement learning, protecting users and society from potential harm. The future of reinforcement learning is bright, with ongoing research pushing the boundaries of what's possible. Advances in algorithms, hardware, and data are enabling agents to tackle increasingly complex tasks. Researchers are exploring new areas like lifelong learning, meta-learning, and combining reinforcement learning with other AI techniques. The potential applications are vast, from smarter robots to more personalized digital assistants. Lifelong learning is an emerging area in reinforcement learning where agents continuously learn and adapt throughout their existence. Instead of starting from scratch for each new task, agents build on previous knowledge, becoming more efficient and capable over time. This approach mimics how humans learn and adapt, opening new possibilities for intelligent systems. Meta-learning, or learning to learn, enables reinforcement learning agents to adapt quickly to new tasks by leveraging prior experience. By understanding how to learn efficiently, agents can tackle a wide variety of problems with minimal data. Meta-learning is a promising direction for creating more general and flexible AI systems. Combining reinforcement learning with other AI techniques, such as supervised and unsupervised learning, can lead to more powerful and versatile agents. Hybrid approaches leverage the strengths of different methods, enabling agents to learn from both labeled data and experience. This integration is driving innovation in fields like robotics, natural language processing, and computer vision. Despite significant progress, many open challenges remain in reinforcement learning. These include improving sample efficiency, ensuring safety, handling partial observability, and scaling to real-world complexity. Addressing these challenges will require collaboration across disciplines and continued research. The journey is ongoing and the potential rewards are immense. Reinforcement learning is transforming the way machines learn and make decisions. By leveraging rewards and penalties, agents can adapt to complex environments and solve challenging problems. From robotics to healthcare, the applications are vast and growing. As research continues, reinforcement learning will play an increasingly important role in shaping the future of artificial intelligence and technology.